if you would recall, yesterday we began the process of bringing integration into our multivariable function land. We did this by looking back at how we could think of integration. Integration is multiplication, but one of the factors is continuously variable. We know that integrals will tell us area under a curve and above an interval on the x-axis. And we just want to adapt that to functions of two variables. So let's dissect the notation and think about what that notation is trying to describe and how we can adapt that to a function of two variables. And then once we get how to adapt it to a function of two variables, adding more variables, not such a big deal. It's like it's a big deal to go from 0 dogs to 1 dog. It's a very big deal to go from 1 dog to 2 dogs. But once you have multiple dogs, adding a third dog is a lot less of a big deal, right? The first derivative is positive, but the second derivative is negative. It's flattening out. Adding more dogs doesn't add that much more logistics once you have multiple dogs. I think the same might be true for human children, but I can't be sure. Memes suggest that it is true. As you talk about like the big deal about the first kid, then you have the second kid. By the time you have the third kid, you're barely paying attention. So those of you who are third kids or later, maybe you can confirm or deny. But let's take a look at the notation again. We have the integral over some interval of f of x dx. This will give us the area under the curve f of x and above the interval I. This is based on area equals length times width, where the length is continuously variable over the width. And that length is represented by the function. The width is represented by the dx. That's the small interval over which we assume the function is constant. So we can take our continuously variable and drop it back to just variable. This will allow us to calculate area using length times width, and then just add up the results, because that's all we're doing with integration. Integration is multiplication, but one of the factors is continuously variable. So integration is just addition. Because addition is just multiplication, but the terms are all different. So we're stuck with addition. We don't get to upgrade to multiplication. What we're asked to do is just evaluate this expression f of x dx at all the points on the interval. Right away, this statement doesn't make any sense at all, because there is no way to evaluate the expression at all the points, because it's a continuum of points. There is no next point on the real number line. It's a continuum. But that's the idea. We're just infinitely plug these points into this expression, add up the results. Once we understand the notation, what the notation is trying to tell us, it's not that big of a deal to upgrade and interpret when we have an integral with a function of two variables. We use the notation should be telling us the same thing. So when we write integral over r of f of x y dA, we know that f of x y is going to be a surface in R3. And so what we'll be calculating here is the volume under the surface and above the region R, in the same way that the definite integral tells us the area under the curve and above the interval. So R here is just a region in the XY plane. It's all the points XY that we're going to substitute into the expression f of XY dA. It has to be telling us that, because that's what the integral symbols told us when we had a function of one variable. So this symbol is asking this set of symbols is asking us to substitute all the values from the region into the expression f of xy times dA. That expression f of xy times dA represents a volume because f of xy is the height. That's our continuously variable height that we're going to flatten out over some small square in the xy plane. So I'm going to call that dA. So I'm taking a height, multiplying it by an area, and that will produce a volume. So we just find all these little chunks of volume for every point in the region and add them up. We're doing the same thing that we did finding the area under a curve. Any questions? Mechanically, it's not even going to be that different. You found partial derivatives. We're going to have to learn to do that backwards, but that's not going to be the big deal. Here's the big deal. An interval is a very simple thing. Start at A, end at B. Very simple thing. That's the only subset of the x-axis. When we only have one dimension to work with, that's all we need. Start here, end here. That's all we need. That's all we get. That's as complicated as it can possibly get because we have a one-dimensional subset of the one-dimensional space. It's just got to be from the start. Once we say we're plugging in a bunch of points from a region, now things are going to get weird. Intervals, very simple. All we need is a start and an end. Regions can be all kinds of things. So intervals, very simple. Intervals, very simple. That's why we never even bothered using the notation integral over I. We just said, let's go from A to B. Let's just always list the interval that way. The start and the end, that's all we need. But now regions can get weird. I can't remember how to spell weird, so I'm going to say strange. I think that counts. If you're in a spelling bee and you can spell a synonym, I think that counts. Because that's like the practical application of the spelling bee. You know what I mean? In other places, are there such things as spelling bees? Or is English like the only language that has such messed up spelling rules that, you know, we actually have to have competitions for it? You know what I mean? Like some languages, the written language, it's entirely phonetic. So if you can read it, you can say it. Right? So if someone says the word and pronounces it properly, you know how to spell it because you just have to put the sounds together. English is not that way because English is stupid. Anyway. I before E except after C, and all the other exceptions. We can't even summarize into dumb rules. English is kind of like integration, which is weird that I like integration more than derivatives. Anyway, that's what's going to be distracting me from now on today. Regions can get weird because we don't just say start here and end here. We don't just need a start and an end because we have two dimensions to work with. A region could be a rectangle. That would be like our simplest case because a rectangle is just two intervals. So that's not very strange. But I've got two dimensions of shape to work with. Maybe you want to plug in everything from a circle. Plug all that into a function. That wouldn't be so bad. So let's give like a little. Yeah, no problem. Okay, now things are getting a little bit weird. This isn't even that weird. I just took the parabola and turned it sideways. That's only weird because we almost always have y equals x squared. We almost never deal with x equals y squared. Poor left and right parabolas, they always get just like tossed out. You're wondering what I was going for. I took the parabola and I just like took that vertical piece and turned it into a sine wave. The trick with dealing with these integrals of f of x, y times dA is that we have to somehow describe these different regions so that the integral can understand. So our job is to describe these regions for the integral. I like to give my integrals sentience. So we somehow have to tell the integral to plug these values or plug all these points into the expression f of xy times dA. The easy part is actually plugging the uncountable infinity of points into the expression. The hard part is telling the integral what values you want to plug in. Now remember, it's a really weird thing to say plug all these values from this continuum into this expression, then add up the results. Because when we think of addition, we think of A plus B, maybe even A plus B plus C plus D, but there's like this discrete set between which we could put plus signs, and we don't have that anymore because we're plugging in all the points from a continuum. There's no place to put a plus sign in between them all. But the fundamental theorem of calculus came to the rescue and said, hey, if you just find the antiderivative, plug the endpoints into that, that will be what you want. So that part taken care of. But we still have to describe what we're plugging in for the expression. Any questions? Really weird for me to ask, are there any questions? Because I'm trying to make you understand what the question is. This isn't a day about how to do stuff. This is just trying to understand what the question is. Is everybody okay? Once we get this process down, then we're going to upgrade things yet again. So looking forward, before we start looking at this in more detail, if I have a function of 3 variables, we're going to interpret this the same way. We have a function of 3 variables. That's going to be, it's not going to be a volume because a volume is a 3-dimensional thing. The function of 3 variables is going to be a 3-dimensional solid, but in 4-dimensional space. So we're just going to take the height given by the function multiplied by not an area, but a volume. So it's going to be f of x, y, z times dv, and that's going to be a 4-dimensional volume under our 3-dimensional solid and above a 3-dimensional chunk in 4-dimensional space. So instead of just line on top, line on bottom, area, surface on top, region on bottom, volume, solid on top, solid on bottom, 4-dimensional volume inside. No problem. Once we can get over not being able to picture it, the number of variables we tack on now, who cares? 8-dimensional volume over this 8-dimensional region to get a 9-dimensional volume. No problem. It's just going to be symbols anyway. Welcome to the game. Let's simplify this tricky part. The simplified version of the tricky part is we're just going to kind of do the same thing that we did with the interval. We're just going to say what's x between and what's y between. That's the oversimplified version of what's going on. What's x between? What's y between? If we're lucky, we'll be able to integrate in pieces. Hopefully, we will be able to integrate in steps. Let's do it one piece at a time. Ew, I don't want to use 4. Ugh. I had to come up with a number, and I got stumped for a second there. I finally settled on one after all that time, and I didn't like it. Immediately, I didn't like it. Let's go with 6. This is going to be our easiest case because I'm just defining a rectangle. See how happy the rectangle is? This is when we see rectangles, we're going to be going, yay! Because a rectangle is just the easiest one. It's just a 2-dimensional interval. X starts at A and ends at B. Y starts at C and ends at D. Our favorites. So the region over which we are integrating, X is from 1 to 5. And Y will go from 0 to 6. There's our region. I said that our hope is that we could just integrate in pieces. What I mean, or integrate in steps. What I mean is, hopefully we'll be able to set this up with an X integral followed by a Y integral, or a Y integral followed by an X integral. So here's what I'm going to do. I'm going to split my integral into a double integral. So I'm going to write 2 integral symbols. Leave space. I'm going to write the function that I'm integrating. And I'm going to break my dA up into a dx times dy. Remember that dx represents that little width, that little piece of the integral, and we flatten the function out on top. Now we have a dx and a dy. So we're just going to make this little rectangle with a dx times dy. That's going to give us a little dA area, a little tiny area. And we're going to calculate the function at some point on that square or rectangle to get the height. That'll make us a volume. F at xy times dA. So the question is, what's x between, followed by what's y between? What is x between here? X is between 1 and 5. So I'm going to say x equals 1 to x equals 5. And that means I'm writing my dx integral first. What am I going to write for my outside integral, my second integral? I'm just going to answer the other question. What's y between? What does y start at? 0. And what does y end at? And so that's going to be my second integral. Notice that the integral and the dx are acting like parentheses. They're acting like a grouping symbol. So I've got this orange integral on the middle, and then the green integral outside. That was the real question. What color was I going to use for the dy part of the integral? It's almost October, so I'm going to combine green and orange. I like the green and orange together. Then if I need a third color, I'm going to use purple. I don't know why. I just like that combination. This is an integral that we can calculate in steps. That first step is going to be the dx integral, and then the second step is going to be the dy integral. So we're going to refer to this as an iterated integral. questions? Yes. That's a great question. That's exactly the question that we're going to look at next. Because so the question was, couldn't hear it on the Zoom. Does it matter which one we put first? Let's find out. What if we didn't look at it this way? What if we said, no, the dy should go first? What would that integral look like? So we'll still need two integrals. Our function is still 3x squared times y. Well, let's suppose that we didn't think dx dy. We're like, oh, nope, dy, then dx. What is y between? Y goes from 0 to 6, and what is x between? Right now you're thinking, well, what if I read it that way? So, excellent question. Does it matter which way order we write the integral? The answer, as usual, it depends. It's not going to matter in this case. Spoiler alert. It's not going to matter in this case, but we won't always just be able to move them around. So we're going to have to do a lot of examples to find out how this actually operates. So it depends. Now, at this point, we have to do some integration to find out this volume, to check to see if these two integrals, which are telling us the same thing, evaluate this expression, 3x squared y dy dx, when y goes from 0 to 6, and when x goes from 1 to 5. Remember what we're trying to do in an integral. Evaluate this expression, 3x squared y dy dx, or 3x squared y dx dy. Hopefully it doesn't matter because this is a multiplication of scalars. It better not matter. And then the integral part is telling you what values to plug into that expression. Now, this is a continuum of values in the x and in the y. So there's nowhere to put pluses in between all these. Fortunately, we have the fundamental theorem of calculus, and we're going to now hope that the fundamental theorem of calculus still applies. Let's look at these two integrals. So I've got integral 3x squared y. X goes from 1 to 5. Let's do the dx, where x goes from 1 to 5. And let's do the dy, where y goes from 0 to 6. So I mentioned that the integral and the d work like a grouping symbol. So that first integral, and the dx, that's like your inner integral. That's the one that needs to go first. We're going to work from the inside out. So first, we'll do the dx integral. Oh, now we're looking at 3x squared y dx. What's the integral of 3x squared y with respect to x? We haven't talked about this in this direction. Where did this come from? We took the derivative with respect to x and landed at 3x squared y. Where did we start? We're integrating with respect to x. So the other variable is just going to be a constant term or a constant factor. If we're integrating with respect to x, y is going to be constant. Is it a constant term or a constant factor? Since y is included by multiplication, y is a constant factor. So the integral of 3x squared y is going to be x cubed y. Oh, sorry, the integral of 3x squared y dx is x cubed times y. If we take the derivative of x cubed y with respect to x, we end up with 3x squared times y. So we just take our derivative skills, our partial derivative skills, and apply them in the other direction. This is a definite integral as x goes from 1 to 5. So we're going to evaluate this as x goes from 1 to 5. This is all still sitting inside the integral dy. We haven't dealt with the integral dy yet. So after we take care of this, we're still going to have to integrate with respect to y from 0 to 6. So here I am evaluating this x cubed y as x goes from 1 to 5. Plug in the endpoints and subtract. So I got 125y minus 1y. Uh, 125 minus 1 is 124. Now we can do the y integral. The integral of 124y is going to be 124 over 2 y squared. So 62 y squared. We have integrated. So we're going to evaluate this over the values of y. Now I have to do arithmetic. 124, 248. So 248 times 3 is 600. and 120, 24. So what's that? 744 times 3 again is 2100, 120 and 12. So 2232. Is it 2232? Did I actually do arithmetic right? I'm kind of shocked. Any questions? Note that I haven't talked about how to do iterated integrals. You already knew how to do iterated integrals because you already know how to do partial derivatives. I didn't even talk about partial derivatives back when we talked about partial derivatives because you already knew how to do it. The other variable is a constant factor or a constant term. The same thing applies now. Now the question is, are we going to get the same thing if we do the other integral? Let's find out. It's the first one. We have to do this to find out. So the integral 3x squared y dy dx. Now here we have y from 0 to 6 and x from 1 to 5. Now we're going to get different stuff in the interim, but it should work out in the same after we do both. First, we're going to do the dy integral. The integral of 3x squared y with respect to y is 3/2 x squared y squared evaluated from 0 to 6. So we're going to have 3/2 x squared times 6 squared minus 3/2 x squared times 0 squared. Now this is still an integral as x goes from 1 to 5 dx. Still an integral as x goes from 1 to 5 dx. So here's where the 0 shows up. So that's kind of nice. And I've got 3/2 x squared times 6 squared. 6 squared is 36 divided by 2 is 18. 18 times 3 is 30, 24, so 54. Did I do that right? Otherwise, it's not going to work. Next, we just need to integrate with respect to x. Now we're down to an integral in just x. So the antiderivative of 54x squared, and I should have left the 3 hanging out there because I knew I was going to integrate an x squared. Oh well. 54 over 3 is, I can't remember. What was it, 18? But we need to evaluate as x goes from 1 to 5. Any questions? See, now what I should have done, instead of multiplying all these out because they don't matter, is recognize there's the 31 in the 62 and there's a 31 in the 124. So I'm pretty sure I've got all the rest of them there. So look for your prime factorization. That's where I should have gone. instead of putting things together, I should have started taking them apart and seeing if the parts all worked out the same. But it looks like I still see this 31 in there, so I think I'm okay. So to answer your question from a long time ago, sometimes it matters, sometimes it doesn't. Now, this was the simplest case. X was an interval and Y was an interval. What we have to do now is change that. What we have to do now is go from the simplest case to the cases where stuff might get weird. It's not going to get this weird that fast. Tomorrow, what I'm going to do is we're just going to do the same integral, only instead of this I'm just going to cut the rectangle with a line. It's going to take a line and go right through that rectangle. And then we're going to have to think about how to describe what X is between and what Y is between. Because now we just have to make more things change. Instead of, if I cut this integral, this rectangle into a triangle, we could still say X is between these two values, but Y doesn't go from C to D. Y has a bottom, starts off at 0, but it's going to go up to this line. How am I going to represent that? All right. That's it for today. I will see you all on tomorrow, and we will do some more double integrals. Everybody have a good day, and thanks for playing.